In this video, we'll discuss polar coordinates and polar graphs. This is a review of material that you've probably seen before. It's traditionally covered in trigonometry or high school pre-calculus. And we'll talk about representing points in polar coordinates rather than rectangular coordinates. We'll discuss the coordinate conversion formulas, and we'll sketch some graphs of polar equations. So here's the idea. We've been sketching graphs in rectangular coordinates. So if I wanted to plot the point x equals 4, y equals 5, I would start at the origin, and I would go 4 units in the x direction. Then I would go up 5 units, and then I would plot that point. And there's only one way to represent that point in rectangular coordinates. But we can tell why this is called rectangular coordinates if we draw grid lines. So I could draw a grid line, x equals 1 right here, that's a vertical line, and x equals 2 here, and then x equals 3 here, and x equals 4 here, and so on. Do the same thing with our y values. We've got y equals 1, y equals 2, y equals 3, y equals 4, and y equals 5. We could draw more grid lines, but I'm not going to. But I think you can see why it's called rectangular coordinates. I sort of follow this rectangular grid. I start at the origin. I go 4 units in this direction, 5 units in this direction if I want to find that point. Well, rather than representing that point in rectangular coordinates, sometimes it's convenient to represent that point in what's called polar coordinates. The polar coordinates can look very similar. What we would traditionally think of as the origin right here, and it's called the pole in the polar coordinate system. And what used to be the x-axis is now called the polar axis. Now, in this new coordinate system, rather than representing a point by an xy pair like this, where we start here and we go x units or 4 units in the x direction and 5 units in the y direction to find that point, or we go x units in the x direction and y units in the y direction to find that point, and we're going to do something different. Let's say I'm interested in this point, and the distance from the origin is r, and the angle that this line segment makes with the polar axis is theta. Well, then that point can be represented by r and theta. So, for example, if r equals, excuse me, let's just say 2 times the square root of 2, I would go 2 times the square root of 2 units from the origin. And if theta equals pi over 4 at the same time, this point can be represented by r theta equals 2 root 2 and pi over 4. Now, I've treated r as a distance from the origin or the pole, but this can actually be a directed distance. We're going to allow r to be negative sometimes. So we'll say that r is the directed distance from the pole. And theta is an angle that we make with the positive, or what used to be the positive x-axis, which is now called the polar axis. Now in rectangular coordinates, there's only one way to represent this point. But because of this theta here, there are actually infinitely many ways to represent this point. I would end up at this same location if I added 2 pi to this angle. So rather than going from 0 to pi over 4, I could go from 0 to 2 pi plus pi over 4. So that same location could be represented by square root of 2 and 2 pi plus pi over 4. Or we could use a negative r value. Now this is the way the negative r values work. Let's say someone gives you these polar coordinates, r theta equals -3 and let's say 5 pi over 6. What does that mean? Well, I would go over here to 5 pi over 6. Now pi over 6, or excuse me, pi is all the way over here on the what used to be the negative x-axis. So we're going to make an angle of pi over 6 here. This isn't perfect, but you get the idea. So there's pi over 6 there. And then rather than going 3 units in this direction, which is exactly where I would go if that was r equals +3 and 5 pi over 6, I would go 1, 2, 3. Now, instead of going in that direction, since r is negative, I'm going to go in the opposite direction. So I'll go out 1, 2, 3 units in this direction, and that's our point. And so you can see from this that r equals -3, theta equals 5 pi over 6 is the same as r equals +3, and theta equals whatever that angle is. There are lots of different ways we could represent that angle. We could say theta is 11 pi over 6. We could say r equals 3 and theta is negative pi over 6. We could add 2 pi to this and keep that negative. There are infinitely many ways to represent that point in polar coordinates. So r is the directed distance from the pole. Directed distance meaning it can be positive or negative, and theta is the angle that we make with the polar axis. Now, when I had a positive r value here, I could add and subtract 2 pi as many times as I want, keep that r positive, and I'll end up at the same place. Now, if I let r be negative, well, that would work if I added pi to my angles. Trying to find a marker that will work in a different color. Okay, so if somebody said, let's let r be -2√2, so we go 2√2 units in this direction. Or, well, actually, let's say it this way. Let's let r be -2√2 and let our angle be 5 pi over 4. So we would go to the 5 pi over 4 line, which is right here. And then rather than going 2√2 units in this direction, we're going to go 2√2 units in the opposite direction. So we'd end up at that location. So this point here is 2√2 and 5 pi over 4. If I add pi to that, well, then I end up over here at 2√2 and pi over 4. Or you could, add pi to this. You'd have 2 pi plus pi over 4, and so on. So there are infinitely many ways to represent that point. R can be positive or negative. And multiplying that r by a -1 is the same as just adding 180 degrees or adding pi radians or subtracting pi radians from the angles. So when I went from 2 pi, or 2 times the square root of 2 and pi over 4 to this one, all I had to do was change that r to a negative value and then add pi. Is it 5 pi over 4? If r is negative, instead of going this way, 2√2 units, we go that way, 2√2 units. So those are polar coordinates. Now, when we're graphing, it's helpful to graph on polar plotting paper. I highly recommend that you pause this video, and if you have access to a printer, just Google polar plotting paper or polar graph paper, and you'll see paper that looks like this. Now you see, if theta is equal to a constant, this is in degrees, but we could have just as easily had it in radians. 30 degrees is 1/6 of 180, so that's pi over 6. This is half of that, so that's pi over 12. 0 degrees is the same as 0 radians. That's 1/4 of pi. That's 1/3 of pi. That's 1/3 of pi plus pi over 12. So it's going to be 4 over 12 plus 1 over 12 is 5 pi over 12. And then we get pi over 2. And so on. Of course, we can have all of these in radians. But if theta is equal to a constant, what we get is a line that passes through the pole. And if r is equal to a constant, then we're saying that that distance from the origin is a constant value. So the polar plotting paper looks like this, whereas rectangular coordinates with grid lines looks like this. So we've got grid lines here, and we've got grid lines here. It makes sense that we would call this rectangular coordinates. I hope you guys see the circular symmetry. If our regions are circles or parts of circles, they're best described in polar coordinates. We'll get back to that later. Okay, so we've got these polar coordinates now that will allow us to represent points in different ways. If we want to convert from rectangular to polar coordinates, this graph is helpful. So let's say we're here at a point xy, and then we're saying in polar coordinates that can also be represented by r and theta. Well, if I draw a little line segment here to the x-axis, this value is just the y value. That distance is given by y. And this value is the x value, so that distance is given by x. And the hypotenuse, that's the directed distance from the origin, which we are assuming is positive in this case. So we'll say that r is on that hypotenuse, and theta is the angle over here. With this picture, we can see the relationship between x, y, r, and theta pretty easily. For one thing, I've got a right triangle. So I know that this leg squared plus this leg squared equals the hypotenuse squared because of the Pythagorean theorem. So I've got x squared plus y squared equals r squared. And also I see a theta here and a y over x. The side opposite theta is y. The side adjacent to theta is x. And remember, tangent of an angle is opposite over adjacent. So tangent of theta is y over x. These are great formulas for getting from x and y back to r and theta. If I know what x and y are, I just substitute them in and then take the square root, and that'll give me r. If I know what x and y are here, I can say tangent of theta is equal to that value. Now you have to be careful. Theta isn't necessarily the inverse tangent of that number. Inverse tangent will only give you angles between negative pi over 2 and pi over 2. It'll only give you angles in quadrants 1 and 2. Excuse me, 1 and 4. So if you want to know the true value of theta, you have to keep the SIGN signs of x and y in mind. If x happens to be negative, so you're over here, well then you can use the inverse tangent on your calculator. That'll give you the wrong answer. And then you can add pi to it so that you end up in the correct quadrant. Okay, so that's how we get from x and y back to r and theta. If you want to get from r and theta back to x and y, we can use trigonometry as well. So those are our first two coordinate conversion formulas. Now, if I know r and I know theta and I want x, well, x is the adjacent side of this right triangle. R is the hypotenuse, and then I've got an angle right there. This X is the adjacent side adjacent to theta that's not the hypotenuse. Now, the identity that I know that's related to the adjacent side is the cosine of that angle. So we can use the fact that the cosine of that angle is adjacent over hypotenuse. Remember that old SOHCAHTOA from trigonometry class? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So we want the adjacent side over the hypotenuse. So that's x over r. And then I can take this equation and solve it for x by multiplying both sides by r. And we find out that the adjacent side is always the hypotenuse times cosine of theta. And similarly, y is opposite theta, so we can use the sine function. Sine is opposite over hypotenuse, so that's y over r. And if I multiply both sides of that equation by r, I get this coordinate conversion formula. The opposite side is the hypotenuse times the sine. Sine involves the opposite, so we get the opposite side is hypotenuse times sine. The cosine of theta formula involves the adjacent side, so the adjacent side is the hypotenuse times cosine. So these two sets of formulas will allow us to convert from x and y back to r and theta, or you can just use your special triangles and your knowledge of trig, your knowledge of pictures like this. I tend to use special triangles. I tend to plot points and then just look for r and theta using my pictures. But you can always use these coordinate conversion formulas instead if that's what you prefer. So let's do a couple of examples. Let's say you're given r and theta, and somebody tells you that r and theta are 8 and pi over 2. Question is, what are the rectangular coordinates for that point? Well, there are two ways you can do it. I think the geometric approach is the easiest. Well, r is the directed distance from the origin, and theta is that angle that we would make with what was traditionally the positive x-axis, but now we're calling it the polar axis. So we go from the positive x-axis to pi over 2. And then we go out 8 units. So this is not to scale, so that's 2, 4, 6, and 8. We plot a point. That's our point. Question is, what are the coordinates of that point in rectangular coordinates? Well, I think we can see that if we're on the y-axis, x has to be 0, and we go up 8 units, so y equals 8. So I would just plot the point like this, and it's a little odd. You actually use theta first to get to that line, and then you go out r units. Normally with an xy pair, I plot x first and then y. Here I'm sort of plotting theta first, or finding theta first, and then finding the r value on that ray. So you can do it that way, or you can use these formulas over here. I know r and theta now, so I can find x and y using these formulas. So there's the alternate approach. X equals r cosine of theta. So that's 8 times cosine of pi over 2. Cosine of pi over 2 is 0. And y equals r sine of theta. So that's 8 times sine of pi over 2. Sine of pi over 2 is 1. So we just get 8. So xy equals 0, 8. Now I know this is easier. We just plug things in and simplify. But I would encourage you to try to think of it this way, because in Calculus 3, your geometric intuition is going to be really important. So try plotting and then seeing if you can read off X and Y like this. That would be ideal. And then confirm your answer algebraically. Because it would be great if you could think this way, think geometrically as opposed to this way. Okay, so I gave you point and polar coordinates, and I asked for rectangular coordinates. We found them. Let's do another one like that. So we have this time I'm given r equals -2 and 11 pi over 6. And we want to find the rectangular coordinates, x and y. Now I'm not going to use my plotting paper just to plot an ordered pair, but I could. So we'll save that for more interesting graphs in just a minute. But to help me, I'm going to add some guidelines here. If r equals 0, that means we're at the origin, or what used to be the origin. R equals 1 is a circle of radius 1, because it's a collection of all points that are 1 unit from the origin, which makes sense. R equals 2 looks like this. And so on. And then our angle is 11 pi over 6. So that means I need to take this and divide it into 12 pieces. So I've got this pi radians up here split into 6 equal pieces. So that means I have to take each of these 90-degree angles and split them into 3 equal pieces. So I'm going to do the best I can. Okay, it's not perfect, but I hope you get the idea. Well, if I took pi and I split it into 6 equal pieces, this would be pi over 6. This is 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6, which is pi. And we've got 7 pi over 6, 8 pi over 6, 9 pi over 6. Go all the way around. And I know these simplify, many of them do. And then we're back here at 0. And we have 2 pi again. But I'm writing it this way just to make it clear exactly what I'm doing. I'm just adding pi over 6 every time as I go from little ray to ray. Okay, so this says plot r equals -2, theta equals 11 pi over 6. So the first thing we do is we go to 11 pi over 6. So that's here. And then if r was equal to 2, I would go 1, 2 units out from the origin in this direction, in the direction of pi over 6. But since r is -2, rather than going this way, I go this way. I go backwards 1 and backwards 2. So we're right there. The question is, well, what is the xy pair that corresponds to that location? Well, for me, it's helpful now to get rid of the polar plotting paper and then just look at it this way. I know that this is 5 pi over 6, or 150 degrees, and this is pi over 6, or 30 degrees. And I know that this distance is 2 because we went 2 units from the origin in that direction. Well, this is a 30, 60, 90 triangle, guys. This is a 1, 2 square root of 3 triangle. If the hypotenuse is 2, the side opposite 30 is 1, and the side opposite the 60 has length square root of 3. Now, since we're in quadrant 2, x is negative, that's negative square root of 3, and y is positive. So the ordered pair xy that represents that point is x equals negative square root of 3, y equals 1. And I know that because of that, my knowledge of right triangle trig. So there are two triangles that you should know from right triangle trig from your trig class. You should know the 30, 60, 90 triangle, and you should know the 45, 45, 90. Now with a 45, 45, 90, or pi over 4, pi over 4, pi over 2 if you prefer, the sides opposite the 45-degree angles have to be the same length because the angles are the same. If these are both 1, the hypotenuse is square root of 2. Now I can multiply all three sides by a constant, and it's just going to make the triangle larger if that constant is greater than 1. The constant is between 0 and 1, it's just going to make it smaller. Same idea over here. This is a 30, 60, 90 triangle. Opposite the 30 is a 1. Opposite the 90 is a 2. And opposite the 60 is a square root of 3. And I can multiply all of those sides by, or all of those side lengths by a constant, and that's just going to change the size of the triangle. But the angles will stay exactly the same. So if I know these two triangles and my trig functions evaluated at my quadrantal angles, so 0, 90 degrees, 180, 270, and then 360, and then of course we want to convert all of that to radians. If I know those two triangles and then my quadrantal angles, I have everything I need to be able to evaluate my trig functions by just sketching a triangle real quick and looking at my picture. Okay, so if you're not comfortable with the geometric approach, if you're saying to yourself, I don't remember that, I don't want to remember that, I just want to take an algebraic approach. Well, we could use an algebraic approach to find this xy pair as well. We know what r is, we know what theta is, and we know that x is equal to r cosine of theta, and y is equal to r sine of theta. So we just replace the r with -2. We replace theta with 11 pi over 6. Oops. Okay. Now for 11 pi over 6, cosine is positive. So we're going to get -2 times a positive square root of 3 over 2. The 2's reduce and we get -√3. And at pi over 6, the sign is negative. So we have a -1/2 there. And a -2 times a -1/2 is a +1. So our xy pair, just through substitution, is -√3 and 1. I still prefer this method, but if you're not comfortable with it, you can always do this instead. But I highly, highly recommend that you try to get comfortable with this and just use this to confirm your graph over here. Okay, so I gave you r and theta and I asked you to find x and y. We could also go the other way. So let's say someone gives you an x and a y. And for each of these, let's find two different representations of the same point in polar coordinates, because we can do that with polar coordinates. So let's say that xy is -3, 0. So we go out -3 units in the x direction, 0 units in the y direction. So we're right there. Well, if r is positive, well, I can see that that distance from the origin is 3, and the angle from there to there is pi. So one way that we could write this in polar coordinates is r equals 3, theta equals pi. We could also do r equals 3, theta equals -pi. Or we could do, let's say, r equals -3, theta equals 0. is then I'd start over here, and instead of going 3 units in this direction, I'd go 3 units in the opposite direction. Or I could start over there. Instead of calling that angle 0, I could call that angle 2 pi. So we're at 2 pi, and we go 3 units in the opposite direction. Okay, so that's one way of doing that. Let's do one more. If I give you xy equals -4, -4, let's say we want to find r and theta. So we're right here. Well, that, since x and y are the same, that angle has to be a 45-degree angle, because x and y are the same here whenever we've got a 45, 45, 90 triangle. So that's got to be a 45-degree angle, so you have to have that 180 plus the 45, or if you prefer, pi plus pi over 4. And we probably should prefer that because we're in calculus class, right? We want to stick to radians, not degrees, even though I still think in degrees. Okay, so in that case, my angle is pi plus 1/4 of pi, so that's 5 pi over 4. And then what's the hypotenuse? Well, if this is 4 and that's 4, I make a little right triangle here, I would take this squared and add them, and that would have to be the hypotenuse squared. X squared plus y squared equals r squared. So -4 squared plus -4 squared equals r squared. That's 16 plus 16 is 32, or r equals the positive square root of 32, and 32 is 16 times 2, so we get 4 root 2. Now that was taking an algebraic approach to getting that hypotenuse. If you don't want to use the algebraic approach, you could just remember this triangle. If this is 1 and this is 1, I get square root of 2 for the hypotenuse. So if this is 4 and this is 4, I should get 4 root 2 for the hypotenuse. And that's exactly what I got down here algebraically. So we can represent that point that way. We could add pi to that, or subtract 2 pi from that. So instead of going to 5 pi over 4, we could use r equals 4 root 2 and theta equals -3 pi over 4. Or we could let r be negative and be on this line segment over here. Well, if that's pi over 4 here, that means this is pi over 4 over here. So if r is negative, theta could be pi over 4. Rather than going 4 root 2 units this way, we go 4 root 2 units in the opposite direction. Okay, so that's how we convert. And again, you can always use your coordinate conversion formulas. I think it's easier to do this graphically. Now let's say you didn't want to do this algebraically, you wanted to do it graphically, or you don't want to do it graphically, you wanted to do it algebraically. Well, you'd find r squared the same way that I did over here. If you're saying to yourself, how would you find theta if we weren't just looking at the picture? Well, I would say to myself, tangent of theta is y over x. So that's -4 over -4, or 1. And then I would use the inverse tangent button on my calculator. The inverse tangent of 1 is pi over 4. Now notice that gives you the wrong angle. The angle's not pi over 4. The angle's actually 5 pi over 4. How would you know? Actually, let's not put that theta there. This implies, well, it doesn't even imply that. So we know that tangent of theta is equal to 1, and inverse tangent of 1 is pi over 4. But x is negative. If x is negative, that means you're in this quadrant or this quadrant, which means the inverse tangent button is going to be wrong. It's going to give you an angle over here, and you want an angle over here. So if x is negative, use the inverse tangent, and then theta will be the inverse tangent of your y over x plus pi, or that's one way of representing it. So we'll have pi over 4 plus pi, which is the 5 pi over 4, which is exactly what we want. Again, we know to add pi because x is negative. X is negative over here. Inverse tangent will never give us the answers over here that we want. Inverse tangent will always give us the answers here. And so we have to adjust by adding pi. If we're in this quadrant, the inverse tangent will give us this angle. Then we'll add pi to it and we'll end up in the right place. If we're in this quadrant, the inverse tangent will give us a negative angle over here. Add pi to it and it'll land you in the right place. Okay. Now you could do the same thing with this. Obviously, if x and y are -3 and 0, you get r squared equals 9. So r equals the square root of 9, which is 3. That's one option. And then tangent of theta is equal to y over x. So 0 over -3, which is 0. And theta equals 0 radians. That's what I would get if I use my inverse tangent button, but my x is negative. So I have to add pi. So we have r equals 3, theta equals pi. So that's the algebraic approach. I prefer this approach. I prefer to just look at a picture and see from my picture what the coordinates should be. Okay, so now let's talk about graphing these functions. I talked briefly about it when I tried to draw my polar grid. Let's justify this a little bit more. Whenever you're graphing y equals a constant, so let's say that somebody just tells you that y is equal to 3, and they want you to graph the function y equals 3. What they're really saying is y equals 3, and x is free to be anything. So x is a free variable. So when x is 0, y is 3. And when x is 2, y is 3. And when x is -3, y is 3. It doesn't matter what x is, y will be 3. And so we get this collection of points. We get a horizontal line, y equals 3. Because x is not mentioned explicitly here, and we're talking about a line, we get the whole thing. We get this whole line, where y is 3 and x is free to be anything. Similarly, if x is equal to a constant, let's say that x is equal to -2, for example, y is free to be anything. So we're saying when x is -2, y could be 0. When y equals 3, x is -2. When y equals -1, x is -2. Doesn't matter what y is, x is -2. And so we get this vertical line. So we have x equals -2, and y is free to be any value. Okay, with that in mind, let's look at r equal to a constant and theta equal to a constant. Now, if r is equal to a constant, let's say r is equal to 3. That is the directed distance from the origin. If someone asks you to graph r equals a constant, they're saying we're 3 units from the origin, or we're this constant number of units from the origin, and theta is free to be anything. So if we're 3 units from the origin, When theta is 0, we're here. When theta is pi over 2, we're here. When theta is pi over 4, we're here. When theta takes on all the values, all the possible values, we get a circle of radius 3 centered at the origin. Now, if r is -3, it actually ends up being the same thing, because if r is -3 and theta is 0, rather than plotting this point, we would plot this point. If r was -3 and theta was pi over 2, instead of plotting this point, we would plot that point. So we would have different values of theta that correspond to each of these points, but eventually, as theta was free to be anything, we get the whole circle. So r equals 3 and r equals -3 have the same graph. So if r equals a constant, we have a circle centered at the origin, with the radius given by the absolute value of r. Now we can also see this result if we just convert this formula r equals 3 or r equals a constant into rectangular coordinates, because we know that x squared plus y squared is equal to r squared. That's our coordinate conversion formula. So if I replace r with 3 or -3, in either case, I get x squared plus y squared equals 9. So I get a circle of radius, absolute value of r, centered at the origin. Again, that's an algebraic approach to this. I prefer a geometric approach, thinking about that directed distance from the origin. I want you to try to start thinking this way, because that geometric thinking is going to be very helpful when you're in Calculus 3. Okay, so that's what we get if r is equal to a constant. We get circles centered at the origin. r equals 1 looks like this. r equals 2 looks like this. r equals 3 looks like that, and so on. Okay, now what if theta is equal to a constant? Let's say that theta is equal to pi over 4, just for example. Again, if somebody tells you that theta equals this and they're asking you for the graph, it's implied that the other variable, r, is free to take on any value. So I would go to the axis, or excuse me, the line where theta is equal to pi over 4. And if r equals 0, we're here. If r equals 1, we're 1 unit out. If r equals 2, we're 2 units out. 3, 4, 5, and so on. And of course, r can take on all of the values between 0 and 1, 1 and 2, 3 and 4. So as r increases from 0 to infinity, we get this ray. Now, but remember, r is also allowed to be negative. So if theta was equal to pi over 4 and r was -1, well, then we would go backward 1 unit. If r was -2, we go backward 2 units. So if r takes on negative values, we have all of these points over here. So if theta equals a constant, what we get is a line that passes through the origin, or the pole, that makes an angle theta with the polar axis. Or if you prefer, if you're like me, you might still be thinking this way, the positive x-axis. Now, if you're saying to yourself, well, how can I know the equation of that line in rectangular coordinates? How can we prove that? Well, we've got this formula, tangent of theta equals y over x. So if theta equals pi over 4, the equation of the line is given by tangent of pi over 4 equals y over x. Well, tangent of 45 degrees, or pi over 4 radians, is 1. So we get y equals x. Now, in general, if I solve this for y, we get y equals tangent of theta times x. So I could be even more specific here. This is a line passing through the origin that makes an angle theta with the polar axis. Or you can think of it as a line passing through the origin with a slope equal to tangent of theta. Now you actually have to have a value for theta there. Theta can't vary at that point. Otherwise we've got a variable times x, and we don't want that. But with a given value of theta, then this is a constant. Or if you want, we can put a theta naught there just to remind us that that's evaluated at a particular theta. Okay. Now, all of this is going to be useful in Calculus 3 because you're going to be integrating over regions in the xy plane. In Calculus 1 and 2, we found area under the curve, what we called area under a curve. So the integral from a to b of f of x dx. By the fundamental theorem, it's f of b minus f of a. Under the circumstances when the fundamental theorem applies, if f is positive, this area is represented by this integral. Well, in Calc 3, you're going to look at something like this. It's going to be volume under a surface. So instead of just having an x-axis and a y-axis, I'm just going to allude to this. It's not important that you memorize this, but I just want you to have a little preview of Calc 3. Every xy pair in some domain is going to correspond to a z value. So every xy down here will go to a z value. And then as x and y vary, we're going to get lots of points, and that's going to give us a surface given by z equals f of xy. If we want the volume above this region R in the xy plane and below the surface, instead of having a single integral, we have what's called a double integral. And this dA will be dx times dy. It's going to be a tiny little area piece in the xy plane. I bring this up because it's so important when we talk about polar coordinates. If this region R is a circle or part of a circle, it's much easier, or it's much more easily described in polar coordinates than in rectangular coordinates. So let's say you're given this region. And this is in the xy plane. Whoops. That's supposed to coincide with the negative x-axis. And this inside circle that's gone is a circle of radius 1, and out here that's a circle of radius 5. If I want to describe this region in polar coordinates, R is going to go from 1 out to 5. Because R equals 1 is that circle, R equals 2 is the next one, R equals 3 is the next one, R equals 4 is the next one, then we have R equals 5, but then actually R can take out all the values in between, so we get all of that. Now, if R was just going from 1 to 5 and theta was free to be anything, we would get that whole washer as our area. But theta is not free to be anything. Theta starts over here and ends over there. So we could say theta starts at negative pi over 2 and goes to pi. That's one way to represent that range of values for theta. This is much more easily described this way, which gives us constant values for r and theta, than in rectangular coordinates. In rectangular coordinates, the equation of this circle is x squared plus y squared equals 25. And so if I have to solve for y, the top half of the circle is the positive square root of 25 minus x squared. The bottom half of that circle is the negative square root of 25 minus x squared. So even though that's not too bad, you just have a polynomial function in x under a radical, like those might be our bounds. Y would have to go from this bottom function to this top function, and they have these square roots in them. If I convert to polar coordinates instead, all of my bounds for my double integral over here are constants. And that's going to be much nicer. Notice the similarity between this and a squared minus x squared. Remember when we did all those trig substitutions? We had to let x equal a times sine of theta or 5 times sine of theta in order to simplify this. Rather than doing the trig sub, when we get to calculus 3, we're just going to switch to polar coordinates and say, I'd rather not look at it that way. I'd rather look at it this way. I'm not going to call that y equals the positive square root of 25 minus x squared and y equals the negative square root of 25 minus x squared. Instead, I'm just going to call that r equals 5. So much simpler. So that's where we're going, and that's why we're studying this. So I just wanted to give you a little bit of context. Okay, now let's look at converting equations, because it's important that we be able to convert equations from rectangular to polar coordinates and vice versa if we want to take an integral like this, which is written in terms of rectangular coordinates x and y, and write it as an integral in terms of r and theta, which is what we'll be doing with polar coordinates in calculus 3. So let's say you're given the rectangular equation x squared plus y squared equals 4 times x, and you're asked to find the equation, the corresponding equation in polar coordinates. Or I guess we would say write the equation in polar coordinates. It's actually pretty easy. All you want to do is replace x squared plus y squared with r squared, and replace x with r cosine of theta. And this is a little unusual. Over here in the xy plane in rectangular coordinates, we often want to get y as a function of x. In polar coordinates, we typically want to get r as a function of theta. Now, this simplifies if I divide out an r. Now, normally I don't allow myself to do that, because if I'm dividing out a variable, then it eliminates the value, it eliminates the value of that variable that would cause division by 0. So if I'm dividing both sides by r, I'm saying, assuming r is not 0, r is equal to 4 times cosine of theta. So that's usually a problem, because it might imply that r can't be 0. But if I look at this equation, I see that there are values of theta that will still give me r equals 0. If theta equals pi over 2, I get 0. If theta equals 3 pi over 2, if theta equals any odd multiple of pi over 2, r is going to be 0. So we're okay dividing that out, because r equals 0 is still accounted for in this equation. So that is that equation in polar coordinates. The idea is just to get rid of all the x's and y's and write the equation entirely in terms of r and theta. And if possible, you want to get r by itself. Let's do another one. Let's say someone gives you x squared plus y squared, quantity squared, minus 9 times x squared minus y squared equals 0. Now remember, x is r cosine of theta, y is r sine theta, and every x squared plus y squared simplifies to r squared. So if I'm trying to write this in polar coordinates, I can replace x squared plus y squared with r squared. So all of that is equal to r squared. And then over here, I've got x squared minus y squared. Since it's not x squared plus y squared, I have to replace x with r cosine theta and replace y with r sine theta. R squared squared is r to the fourth. And over here I've got 9 and an r squared cosine squared theta and an r squared sine squared theta. And if we factor out an r squared, we get this. I can factor out r squared again. And this times this equals 0 if this equals 0 or this equals 0. So either r squared equals 0, equals 0, or r squared equals, if I add this to the other side, 9 times cosine squared minus sine squared of theta. Those are both like functions of theta. You probably don't remember this trig identity, but cosine squared minus sine squared turns out to be cosine of 2 theta. So r squared could equal 0, or r squared could equal 9 cosine of 2 theta. Now, I don't want to rule this out unless r squared equals 0 is possible over here, and it is. R squared can be equal to 0 every time 2 theta is an odd multiple of pi over 2. So that's whenever theta is an odd multiple of pi over 4. So I don't really need this case. That case is actually included in this case. So we're good to go. We'll still get r equals 0 over here for certain values of theta. And if we want to get r by itself, I guess we could take a square root. Because if we're saying that r squared is equal to this, we're assuming that this is positive. So that makes sense. So that is the simplified version of that equation. Now, that you might say to yourself, that's not very simple, but it is simpler than this. Do you want to solve that for y, like we did up here? I don't think so. It's going to be a pain to solve for y. This one's not so bad. We could solve it for y. We'd have y equals the square root of 4x minus x squared, plus or minus the square root of 4x minus x squared, but instead, say, hey, r is just 4 cosine of theta. That's pretty simple. So in both cases, I think this equation is simpler than this equation, even though it introduces a trig function. Cosine of theta isn't too bad. And this equation is more complicated, but I don't think it's as complicated as this one. So I think I would rather, if I'm working with a curve like this, maybe in the xy plane as part of a bounds for a double integral, I might prefer to write the equation of that curve this way as opposed to this way. Okay. Now you could be asked to go the other way. So I could give you r as a function of theta and ask for the rectangular equation. Now this one looks tricky, but it helps to rewrite that secant of theta as 1 over cosine of theta. Now if I multiply both sides by cosine of theta, I get this. Well, that's nice, because I want to write everything in terms of x and y, and x is r cosine of theta. So this is just the vertical line, x equals 3. Now I'll just draw the solid line because that's what we're graphing, isn't it? Now x equals 3 has two representations. It's r equals 3 secant of theta and x equals 3. Wouldn't you rather stay in rectangular coordinates for that one if x is equal to a constant rather than r equals 3 secant of theta? I think I'd rather stay in rectangular coordinates for that one. So if I had some bound like this, I might say, hey, let's convert it to rectangular and see if it's easier, more easily described in rectangular coordinates or polar coordinates. Here, rectangular coordinates is better. Here, polar coordinates is better. And here, polar coordinates is better. Let's do another one. Let's say r is equal to 4 over sine of theta plus 2 cosine of theta. That also looks very complicated, but if we multiply both sides by that denominator and distribute the r, look what we get. That's just y plus 2 times x equals 4. Because remember, y is our sine of theta, x is our cosine of theta. So this is just the line y equals 4 minus 2x. When x is 0, y is 4. When x is 2, y is 0. Wouldn't you rather describe that one in rectangular coordinates? It's just a line rather than polar coordinates? I think I would. So if I see an equation like that, I might say, oh, let's convert to rectangular. Generally, if you're seeing lines, you probably want to stay in rectangular coordinates. If you see circles or circular sectors like this, it's going to be easier to describe in polar coordinates. Now in the next video, we are going to graph some polar equations. I was going to do that in this video, but I've run a little long on time.